Hello DE students, this week we are moving into 4.1.1, which is state machines. This instructional video is going to be broken into 4 different parts. Part 1 is going to focus on defining state machines and looking through their block diagrams. Part 2 is where we are going to discuss a few examples of state machines. Part 3 is where we are going to look through the steps it takes to create and design a state machine. And then part 4, we are going to overview an example of a state machine. So let's get started. Okay, so for part 1, we are defining state machines and illustrating their block diagrams. So a state machine is a synchronous sequential circuit that has a combinational logic section and a sequential logic section. A state machine uses a combinational and sequential logic to make decisions on outputs based on the inputs. The outputs and internal flip-flops go through a predictable sequence of states in response to clock signals and other inputs. And a state machine will hold a state until a new set of inputs are given, those being either from the flip-flop or the clock signals. Okay, as mentioned on the last slide, a state machine will hold a state until a new input is provided. This task is completed by having 3 distinct sections of the state machine. There is the input of the combinational logic, the memory, which is made up of flip-flops, and then the output of the combinational logic. The flip-flops in the memory section of the circuit are what determine the number of states that we have and transition our circuit between the states depending on what inputs they receive. So to review, when we're talking about a state machine, we're essentially talking about a flip-flop sandwich where we've got combinational and sequential logic on either side, and the flip-flops are what are controlling the states. The inputs from either a clock signal or the flip-flop are what transition us between the various states, and the amount of flip-flops are what determine how many states we have. Now that we've defined a state machine, let's look at some examples. So 3 examples of state machines that we can take a look at are traffic lights, garage door numeric keypads, and vending machines. I want you all to take a moment to think. What do these very different items have in common that allow them all to be run by state machines? I want you to then go into Google Classroom and provide your answer to the question that I've posted there. So now that you've all taken a minute to go over to Google Classroom and put in your thoughts as to what the traffic light, garage door numeric keypad, and vending machine have in common, we can talk about it a little bit. Specifically, all of those devices are based on a set of sequences. A traffic light, green, yellow, red, green, yellow, red, over and over again. Now, the numeric keypad and the vending machine work a little bit differently, but they're still looking for a specific set of sequences in order to create a certain output. On a numeric keypad for a garage door, you have to type in a certain code in order for the garage door to unlock. If you don't type in that sequence of numbers, you don't get the output that you want. Now, lastly, the vending machine, a little more complicated. There's a lot of different outputs that we can have there based upon the inputs from the user. Bag of chips, pack of cookies, they're all different inputs. However, that state machine and those flip-flops on the interior are able to take those sequences, those inputs, and therefore set the state to a specific output. So that's why they all run on state machines. Okay, so now we are going to look at part 3 of our lesson, which is on state machine design. There are 4 basic steps to designing and creating a state machine. The first is that we have to create a state graph. The state graph identifies the number of states that we have as well as the number of state variables, which essentially is how many flip-flops we need within our circuit. We then are able to label our outputs and encode those outputs to the various states. Once we've created that state graph, we then have to create a state transition table. That state transition table is going to look a little bit similar to what we've done with K-mapping, but it's going to allow us to write and simplify our design equations from the original circuit. And then it's going to allow us to design our circuit with our simplified logic. So a state graph shows the sequence of states that the state machine will transition to on each clock transition. And this is an example of a state graph with 4 states. We are going to study this state graph in detail later. Right now, I just want you to focus on the parts of the state graph and how they are related as I continue through the next few slides. So here we see that each state bubble is labeled as S0, 1, 2, or 3. These labels are arbitrary, but they do help us track what state we are in. And then each transition arc is labeled with the values of the input variables that make the transition occur. So if we look at the transition arc here, we can see that these inputs are what either cause the transition or cause the state machine to hold the state. So here, this is a closer look at those different pieces of the state graph. So the state variables are the outputs of the flip-flop. So they're typically labeled as QA, QB, QC, QD, etc. And they are located right here. So these are our state variables. We've already discussed the state bubble and our transition arcs. We have two different ones. We have one up here and one over here to the side. Now, the number of state variables is determined by the number of states according to the following function. So the number of states is less than or equal to 2. For example, 2 states requires a 1-state variable. 4 states require a 2-state variable. 8 states require a 3-state variable, and then 16 states would require a 4-state variable. There will be an occasion when a design has unused states. For example, if your design requires 6 states, you will only need 3 state variables. Thus, there will be a total of 8 states, but only 6 of them will actually be used. Each state is assigned an output value for when the state machine is in that state. So the state variables are actually the outputs of the memory flip-flops. And for that reason, like I said before, they're labeled QA, QB. So this 4-state example would require 2 flip-flops for QA and QB to clock through 4 different states, S0 through S3. And then looking at the output variables, each state bubble is assigned to output variables as well. This example has 4 output variables based on what state it is in. So after we've created the state graph, we need to turn it into a state transition table. This process could be compared to K-mapping in that we have to transition our maps into logic statements. So you'll see that we have 2 lines for each of these, and they are transitioning over from the different state bubbles into this graph. So the state transition table is meant to describe the present state and the next state that's associated. So you're going to notice that each state occupies 2 lines on the state transition table. That is because in this example, each transition is triggered by only one of the 4 possible inputs at any time. In a state machine, the next state is actually the output from the memory flip-flop, so QA and QB, when an input is changed. So QA is DA for the next state on one flip-flop, and QB is DB for the next state on the other flip-flop. The outputs from the memory flip-flops are linked to the input combinational logic. That way a transition is made on the next clock signal to the next state. So again, we have that clock sequence. Now that we have a state transition table, we can create our unsimplified expressions for the input combinational logic and the output logic. So what we're looking for is our logic to be synced between our inputs and our outputs. And then we end up with our design equations. So to summarize part 3, to design a state machine, we have 4 basic steps. We start with a state graph, then we move into a state transition table. After we have that state transition table, we simplify our logic, and then we design our circuit. All of those sequences have to happen in that order. That state graph is really important, and making sure we transpose it over to the state transition table is equally as important. Now that we've talked about that, let's move into an example and take a look at how a state circuit is actually designed. Okay, so this is going to be the 4th and final segment of our state machine lesson, and this is to walk through an example of a state machine design. So the scenario for this design is that a state machine will count out the last 4 digits of a phone number only when an enable push button is pressed. The output should hold the last number until the enable button is pushed again. So the example we're working with is the fake phone number 585-476-4691, and our display is going to be 4, 6, 9, and 1. So whenever the enable is a logic 1, the outputs will continuously cycle through the four values of 4, 6, 9, and 1. And whenever the enable logic is 0, the outputs will hold at their current values. So for this design, any form of combinational logic can be used, but the sequential logic must be limited to D flip-flops. So step 1 is to create our state graph. And this design has only one input, and that's the enable button. So each state bubble should have 2 transition arcs, one for the enable 0 and one for the enable 1. So you can see that there. Step 2 is to determine the number of state variables and assign them to the various states. So with 4 states, this design requires 2 state variables. These state variables are labeled QA and QB. This labeling is arbitrary, but does use the recommended Q notation since they're flip-flop outputs. And then the 4 combinations of the 2 state variables, 0, 0, 0, 1, 1, 0, and 1, 1, are assigned to those 4 states. And that's what you see there. So in order to display the output in binary, we encode from base 10 output and count into base 2, which is the binary. Because the largest output count is 9, 4 output variables are needed to represent this number in binary. So 9 is equal to 1, 0, 0, 1. These output variables will be labeled C3, C2, C1, and C0. Therefore, as an example, in state S0, the output 4 is encoded into binary would be 0, 1, 0, 0. And then you need to repeat this process for the remaining 3 states. So then for step 4, we have to create our state transition table. So this is our state transition table for the design example. Each state has 2 lines on the state transition table, 1 line for the enabled equals 0, which is our hold state, and then 1 line for the enable equals 1, which is the transition to the next state. You need to note that even though the EN may have been switched from 0 to 1 in the first 2 lines of the table, the encoded output does not change until the clock signal transitions the circuit to the next state. The encoded outputs for both lines of S0 are the same. So you will designate the next state QA, QB on the output side of the table, but you do not change the encoded output. So just imagine that the clock signal occurs when you reach the far right of the table and can then move down to the next line with a new encoded output. So here we can see that we have now written and are simplifying our design equations. Now, here we need to ask ourselves, is this as simple as it could get? So this is then when we take our AOI simplified logic and we design that circuit. So take a moment and ask yourself, is there a better way for us to implement the logic for DB? And why or why not? There is a question in Google Classroom for you to answer about this. So please take a moment to look at this slide and make sure and see if there is a better way to implement DB. So the answer is yes, we can simplify this further. So by simplifying further, we can then alter our AOI logic, and this is actually our simplified further, which gets us with the use of the XOR gate. So then on this slide, we see the mapping of the final state machine design to the general block diagram for a state machine. The final output from the state machine can then be input into a BCD 7-segment decoder. This will allow the phone number to be viewed on a 7-segment display. So that's what we are looking at here. Down here we see our basic block diagram, and then this is the logic and how it would feed into our binary outputs here. We could then, of course, add a 7-segment display into that. All right, so now you've seen a walkthrough example of how to design a state machine. You are now going to have an assignment in Classroom where you need to access Multisim Live and a tutorial video to wire up a state machine and get some observations from it. So check out your assignment in Classroom, and I'll see you guys soon.